Okay, Bismillah ar-Rahman ar-Rahim, wa salatu wa salam ala ashraf al-mursalin, Sayyidina Muhammad, wa ala alihi wa sahbihi ajma'in. Assalamu alaikum, everyone. Topic 5, last topic of the course. Okay, so we're done with the talking about control on SO3 and SA3, and then, as an application we looked at last time, having drones. Today, inshallah, and in this last part, we're going to be looking at robot manipulators. We're going to come back to these serial linkage robot arms. And then we're going to look at two problems. The first one is doing motion control, which is simply making the robot move from one place to the other, as in the arm itself, have some configuration from one configuration to another. And then we're going to be looking at using that robot arm to do something, not just to move around, but also to interact with the environment. And this will be the last couple of lectures in the course, inshallah. Okay, so let's start with the discussion first about the open loop analysis of that system. So first we're going to be looking at the open loop analysis, then we're going to be looking at stabilization control, then I'll contrast what we're going to be doing in the stabilization part to what's known as the feedback linearization, which some of you might be familiar with. So these are the equations of motion of an N-link manipulator, just to remind you that M of theta, so here theta is the configuration. So for an N-link robot arm, theta would live in a configuration manifold. We're going to be calling it Q. And this configuration manifold, assuming we have just revolute joints, so every revolute joint lives in S1, where S1 is simply isomorphic to minus pi to pi. So S1 is the circle. So we say it lives in S1 cross X1 cross X1. And this is simply the N torus, as we've seen earlier. And the equations of motion on that, for that configuration, we've derived it earlier using the recursive Newton-Euler formalism, if you remember. And there are many ways. You can even derive it using Euler-Lagrange that you should be familiar with. So it will give you in the end M of theta, the mass matrix, multiplied by theta double dot, C of theta and theta dot, which is the Coriolis and centripetal forces, torque, multiplied by theta dot. And then you have here, we add something that we haven't added before, but it's trivial, which is simply friction. You can have a friction as a function of theta dot. So assuming that in the links themselves there is some friction. And here we model it to be non-linearly as a function of theta dot, which is also possible. You can model in this way column friction and other types. Multiplied by theta dot, and then you have G of theta, which are the gravity torques. And then you have the tau, which are the control torques that you have, that you would like to apply to the robot arm using some motors in this case. Yes, Fahd.
Okay, so if there's a term that's in a higher velocity, like for example, a function of v square and v part,
Yeah.
is it in the v theta?
That's right, yeah.
Coriolis?
No, in the B of theta. So if it comes from friction, something that dissipates energy, then you put it in the B theta. Because everything in the C here, they don't contribute to the energy balance. That's usually how it goes, okay? They're fictitious torques, actually, okay? They're not real. We've looked at it earlier that we can put this equation of motion, okay, written as a second order differential equation, into the state space form if we define state 1 and state 2, x1 and x2, to be theta and theta dot. Theta and theta dot together lives in the tangent bundle of this configuration manifold. And the equation of motion, if you take this equation, you can put it in this form. Okay, so we've seen this before, so this is not something new. Just as a way to simplify stuff, so you can call B, the capital B as a function of theta dot multiplied by theta dot. You can call this small b as a function of x2. The same for C, which is a function of theta and theta dot. Here multiplied by theta dot, you can just combine all of things here to be this small c. Okay. And just to remind you, if you looked at the tutorials, the MATLAB tutorials specifically, then we've seen actually that earlier that the C matrix itself, factorizing the C itself and writing as a matrix is not unique. You can have many ways to write it. However, when you multiply everything together and you get this C of x, it becomes, okay, this is actually not unique. However, this is unique, okay, written in a torque format. And the first thing before moving on to do the control and stability and so on, let's look at just the open loop analysis. So let's take the system and look at the equilibrium points. So we're going to put tau equal to 0, which means that we're going to be looking at the open loop, the performance of the system. And the equilibrium points of any N-link manipulator, they would satisfy that you have x1 theta, x1 star and x2 star satisfy the following. x2 star is equal to 0, and x1 star when you plug it in the G, you get 0. Okay? And this already automatically follows from this equations. You can very easily, this is actually part of your assignment, you had it earlier. So if I want x1 dot and x2 dot to be simultaneously 0, then x1 dot implies x2 equal to 0. And if x2 is equal to 0, and this part goes away, and the torque here we're not talking about it, so I'm left only with m inverse multiplied by the c, but the c itself was a function of theta dot, okay, linearly. So if theta dot is 0, then all of the c also terms go away. I'm left only with the m inverse multiplied by the g, okay? And this should be equal to 0. The m inverse itself is, the m is positive definite, which means that the m inverse is also positive definite, which means that it cannot be equal to 0, then the g itself must be equal to 0. So that's simply what this term means here. And of course, what I just mentioned here is simply written here as a proof. Okay, you can read at your own pace. So, and that's what we've been doing in the assignment. So in order to identify what are the configurations that would be valid equilibrium points for an n-link manipulator, they are simply the configurations that have 0 velocity. Okay? So at that configurations, the joints are not moving. And at the same time, you should counteract gravity. So when you plug in, so the gravity should not act on them, should not produce any torque. This is exactly what this G of x1 star means. Okay, and when you had, for let me see, we don't have an example here. Okay, yeah. So the two-link manipulator. So this was what you had in the assignment. So this was the gravity torques as a function of theta. Okay, they were given by some constants, gamma 1 and gamma 2. They're all positive, but they were a function of theta 1 and theta 2 in this way. And then to solve for the equilibrium points, you simply have that these should be equal to 0, but also that should be equal to 0 at the same time. So you should have that sine of theta 1 plus theta 2 should be equal to 0, and sine of theta 1 is equal to 0. And then you can see that if you only look at the region from minus pi to pi for the two joints, then we have 4 solutions. We have either 0, so theta is equal to 0, 0. So the first link is 0 and the second link is 0, so the bottom down configuration. The second configuration is that the first link is 0 and the second one is upside down. Okay. The third one is that the second link, so the first one is upside down, but the second link is 0, and the fourth equilibrium point was both of them are upside down. Okay. You had something like this to play around in the assignment. Okay. So this is just, in general, by the way, this holds, not just for two-link manipulators. It's easy to play around with it, but in general, this holds, and it depends on how your robot is actually configured here. Okay. Make sense so far? So this was the analysis that we've seen, and let's now move on and look at, okay, dynamically what will happen. So let's start by doing a Lyapunov analysis for the system. We're going to be choosing the total energy of the system as the Lyapunov function. What is the total energy of an n-link manipulator? You simply have kinetic energy and potential energy. Kinetic energy is given by that expression. It's half theta dot transpose multiplied by m of theta theta dot. Okay. We've seen how we can derive this expression earlier from the rigid body dynamics, the kinetic energy of each individual rigid body, and you sum them and use the Jacobian and so on. So you can go back to topic 3 for that expression. Where did we get it from? And the potential energy, we never talked about it, okay? And we never mentioned actually that the gravity itself, the gravity torques, they are given by the gradient of some potential energy with respect to theta. We never derived the gravity torques like that. If you remember, we looked at, for example, having the gravity as an external wrench at every link at the center of mass, and then we combined all of that, okay, into some torques that we call the G. And another way to talk about gravity, we said that gravity itself, we can think of the inertial frame itself as accelerating. And the third way here to look at gravity is simply that you can define potential energy, okay, function, and you take the gradient of that potential energy function with respect to the theta, and these will give you the gravity torques. Okay? And this is not new for you. You have always heard about that actually gravity as a force is usually the gradient of some potential energy. So you've been told that gravity is, is a conservative force. It does not, dissipate energy and so on and so forth. Okay? Does it make sense? So, so if we want to consider, the stability analysis of the manipulator just, swinging around, you can simply take an open loop Lyapunov function to be the total energy, which is the kinetic energy plus the potential energy. And in order to be a positive definite function, we need to check, okay, is this positive definite or not? The first term is easily quadratic. Okay, so you see it's already x2 transpose multiplied by m of x1 multiplied by x2. M is positive definite, which means that this whole term is positive definite. Then we're left here with the potential energy. The potential energy, you can assume, okay, it just increases, okay, because the robot cannot reach infinite heights, and it cannot, its bottom, it's bounded from below, it can only be zero, so it's still positive definite. Okay, so with some extra analysis, you can show actually it is positive definite, and most importantly, it's actually zero. Okay, so the whole function is zero when the energy is zero. Okay, so if I'm not moving, okay, then I don't get any energy component. And that's left for you as a homework. Okay, it's not that hard to show. It's like very easy. That actually, if you compute the v dot of the total energy along the trajectory of the system, so you compute the gradient of this term multiplied by x2 dot, gradient of that term multiplied by x1 dot, and you just play around with the equation that we've seen before. You're going to be using a certain formula, okay, a certain property that's very important, but we don't have time to go into details of it, and I'll mention it in a bit. And using that formula, you can show actually that v dot is equal to that stuff. That's not negative definite, it's only negative semi-definite as usual. You can use on Lassalle's invariance principle and so on and so forth. You can just keep on doing the same drill that we've done before. The formula I mentioned that you're going to be using here in the homework.
The potential energy relative, right? Not absolute, right?
Yeah, from the home configuration, yeah.
From the home configuration.
From the lowest configuration, because you can choose also the home configuration to be something on the top. So you can also do that.
I define this relative to what?
Yeah, exactly.
Home or lowest one?
Exactly, yeah. No matter how the thing is, no matter how the E potential is, it will always be such that the gradient of it is equal to G. And that's the whole idea. You can think of it this way. I don't need to say what the E potential is. I only need to say that when you take a gradient, I get the G. So implicitly, it's defined by that. You can think of it another way. If I know the G, I integrate it, I get the scalar function, right? So I don't need to tell you what the scalar function is. You can just know already that it's whatever function that I take the gradient of, I get the G.
So okay. Whatever, for example, if I get the reference also will give me it is positive or negative G, right?
The G is always, yeah, so depending on the home configuration that you chose, the G might change, okay? So G is always a function of theta. So you give it the theta, it will tell you what the torques are. Some of the configurations will have zero torques, right? There is no gravity torque that will start to move it. For example, exactly the ones that we talked about when we talked about the equilibrium. Okay. The formula that I mentioned that you will be using here in the homework, it's actually a very important property of manipulator dynamics in general. And if this is the equation of motion of a manipulator, okay, it's always valid that m dot is equal to C plus C transpose. Okay, so m dot, so the rate of change of the mass matrix, because this is the function of theta. Okay, so the rate of change of this mass matrix with respect to time is equal to C plus C transpose. Another way that you're going to see it a lot in the literature is that m dot minus 2C is a skew-symmetric matrix. And this property alone is already enough for you to do the Lyapunov analysis. Okay. So this is some stuff that you can look at your own pace, and if you want to explore more, if you're interested in robotics, but this is a standard formula, okay? But there's a lot to say about it, especially from a geometric point of view, but we don't have time to go into that point, okay? So that's it for the open loop stability analysis. So the whole idea of what I want to highlight here is that as long as you have, okay, friction, okay, as long as you have friction, you have gravity, I take the robot arm, okay, and I leave it. What happens? Just keeps on swinging around. It's a serial linkage, right? So 2 link, 3 link, 10 link, doesn't matter. It just will keep on swinging around, and then the friction will make it what? Will make it eventually stop in the end. And thus, this is the physical way of looking. So this is the analytical way of proving that the bottom configuration, where all of the links are just hanging down, is asymptotically stable. Okay, And provided I don't start exactly at the configurations where gravity doesn't play a role, for example, the other equilibrium points, the robot arm will always fall on the ground. Okay? Now I'll give you something for those of you who had some practical experience with robots. Why don't we, when we turn on the robot, why doesn't the robot arm just fall around and prove this theory? First of all, there are brakes. Okay? So whenever you turn on a robot, okay, you're usually going to have brakes. And even if you turn it on, you're going to find that it's not that the torques are given by 0. So here, all of this analysis we did, the torques that are usually, so you see all of this analysis that we did here, assume the first thing we do, we're talking about the open loop. So torques are equal to 0. There is no torques from the actuators themselves. Okay? However, first thing that you can apply brakes from the actuators. You can prevent the robot arm from falling. That's one thing. The second thing is that even the motors themselves, they can have gears inside, right? And they can be very heavy, and they can prevent from going. But not that that clean, okay? But still the brakes, the joints themselves, they can have much more dynamics that you're not taking into account. Okay, the easiest thing to be just the brakes. Okay, so that does make sense. Okay, so the whole intuition that I want you to get from here is that this is the very easy analysis that you can do to prove actually that any link manipulator will just keep on falling down. With this information, what we want to do now is we want to make the robot arm have a certain configuration we want. We want to do stabilization control. We don't want it to just fall down. Okay, we want it actually to go to a certain configuration. So what we're going to be doing today, inshallah, is stabilization control of this robot arm for an N-link manipulator. Okay, we're not going to be taking the two-link. I'm going to show you in the end software implementation of the two-link manipulator arm. However, what we do here is generic for any robot arm. Okay, provided the assumptions we're going to be making. So how do you think we're going to be tackling the stabilization control? So what comes into your mind? Okay, so it's a nonlinear system, highly nonlinear. What do you think how we're going to be solving the problem? PD control. Okay, so nothing else. Okay, so it's your bread and butter as a mechanical engineer. Okay, or in general, as I mentioned, I think there was a question before by Noman. Why is PD control very powerful? For the same reason. Okay, because mechanical system already has its own inertia and it has all the damping and so on, and the PD controller will make whatever as a baseline controller it can take you in a lot of places. So our energy, we're going to be designing an energy balancing controller, so a PD controller in the end. So such that we want to have a state, that's a desired state that has theta desired and 0, okay, to be asymptotically stable equilibrium point of the closed loop system given by that expression. Okay, so what I just did here is I plugged in the tau equal to tau p plus tau d. How do we design the proportional term and the derivative term? Same idea. The proportional term will become from the gradient of some positive definite function that you choose, psi of theta, and you design it such that it has a minimum at theta equal to theta desired, and you inject the damping with the derivative term such that the closed loop system, the closed loop energy function or the closed loop no function is negative definite. Same idea. Will this be harder? So we have an N-link robot arm. Will this be harder or easier than looking at SO3? After what we did in SO3, this will be a piece of cake for one simple reason. What is it? That our configuration manifold is given by the N torus, but the N torus itself is isomorphic to Rn, right? If I say I have from R, from minus infinity, from minus pi to pi, so in the end I can just work in Rn, and that's exactly what you've been always thinking about. A configuration manifold of an N-link manipulator is Q1, Q2, Q3, and Q4, so in the end they're just Rn. Okay, so doing stuff here will be a piece of cake, okay, compared to SO3. Okay, so things will be really easy. But however, the same generalization of PD control that we did is also valid here. Okay, and it will also make our analysis of this controller very easy. Okay, so that's a bit for today. So we're going to go to the board, and I'm going to show you in the end that we're going to be deriving a proportional term given by this expression. Okay, we're going to be deriving a derivative controller given by that expression. We're going to be putting stuff in the closed loops, in the closed loop dynamics. We're going to be showing that this has a global asymptotic equilibrium point, and then afterwards I'm going to show you the software implementation of this on MATLAB so that you can play around with it. Okay, so let's go to the board. Any questions before we start?
There is another method like feedback linearization or computed torque. So okay, this is what will.
Yeah. So after I tell you about this, I'm gonna go to feedback linearization. Okay. Whiteboard. Sorry? Yeah, thank you. Okay, so let's see. Okay. Okay. So we're going to be doing PD control or stabilization control on Q, okay, which is simply isomorphic to Rn. So our objective is to stabilize the system at xd equal to theta dn 0. Okay, we're still doing stabilization. Okay. And our controller, our control law will be given by this expression, tau is equal to tau proportional plus tau derivative. And to start, we need to define an error function, an error between the theta and theta desired. Any ideas? What is the error?
Change R.
So how do you take an error between two RNs? Theta minus theta desired. That's it. So theta error is simply defined as theta minus theta desired. Of course, this is valid because everything is Rn. Even if I have this torus, right? But the torus is also, if I just restrict from minus pi to pi, it becomes just Rn. Okay. You have to be careful now, and this is the tricky part. Okay. You can do it also in a more fancy way, but you need to be careful that when I have, for example, 180 minus 179. So if this is 180, right, and this is minus 179, the robot should not go all over the place. So you should have. It's not a thing. Yeah, it's this issue that we're simplifying stuff with Rn, but still you can easily make a workaround. Okay, no need to complicate stuff here.
Theta here, it is only scalar or vector?
No, it's a vector. It's theta 1, theta 2, theta 3.
But we say that it belongs to manifold.
The torus, yeah, exactly. But the torus is isomorphic to Rn.
The torus
is isomorphic to Rn. So in the end, things are easy.
So what about SCE3 and SO3?
They're not definitely. They're locally Rn. Okay, locally look like Rn, but globally not. Okay.
And the torus it is not related to SC3.
Sorry.
And the torus it is not related to SC3.
No, it's completely different manifold. The torus was a 2-dimensional manifold. SE3 is a 6-dimensional manifold. No relation. Yes, ma'am.
Okay, I just forgot that the torus is Rn.
Yeah, torus is Rn. Right? Remember when we plotted the torus as the surface of a donut, but also we made it into just R2. But you have to restrict only from that you're from minus pi to pi. Okay? So to be properly speaking, we're not the value of theta doesn't take from minus pi to pi. However, it's just we have the fact that from minus pi to pi you can add stuff. I can take, so for example, angle equal to 20 minus 3 is 17. So I can do this minus. So okay. So however, at the point when you have all of this, the chart that that you need to change the chart, you need just to play around with it to make sure that it works. Okay.
So we said locally it's Rn, right?
SE3.
No, yeah, the torus shape, that topology, I mean.
Locally it's Rn. Yes, yeah, exactly.
The question I'm not really getting is how can we say that no, we cannot say that in this case it's not Rn. What kind of motion or what kind of control could we do that we cannot say that no, we cannot say it's Rn.
The thing that makes the configuration manifold here from Rn to Tn is simply you identify it is a plane. However, this line and this line, they are identified like that. Okay, and this line and that line, they are identified like that. Okay, so in the end, it's like everything is really just I have vector algebra, right? I can do linear algebra, especially but not only at the at the boundary, exactly, at the boundary of how you cut how you cut the plane into, or how you cut the cylinder or the end torus into the plane. That's the whole idea. Okay, so in order for, not to make things a little bit complicated, let's look at it as Rn. Things will be exactly the same, and you're going to see even in the implementation, we're not going to have any issues there. Okay.
You mentioned that there might be a problem if the angle is like 180 and minus 170.
Yeah.
How do we tackle that?
You can take the minus sign and just do what's known as a wrap the angle in the end.
What do you mean by that?
Wrap the angle. So if I have, let us take a scenario for 180 minus 179.
Yeah.
Okay. So I have 180 minus 179. What's the angle? What's the angle error? From the number, from Rn.
From the number it would be like 359.
359.
Yeah.
Now module that by 360, what do you get?
1.
So that's 1.
So
So the error is 1.
we basically take it out of 360, so it becomes 1.
Exactly. So it's very easy, just to fix it and then to fix this issue. There's no need to actually to do geometrically. We don't have this idea of, no need to look at the tangent spaces and take stuff, from the tangent space to the algebra and play around with it. It's simple as that. Okay. And inside of the region, we still have minuses and pluses. They're all valid.
But I remember in the previous lectures here that you mentioned that each joint could be represented as isomorphic to SE3.
Every joint to isomorphic to SE3? No.
No?
No.
So here we can say that in the configuration level, we can make it isomorphic to Rn.
That's right.
In the workspace,
Exactly. The workspace is not.
no.
And that's exactly what we're going to be looking at in next time,
So
when we look at the impedance control. Absolutely. If you want to do stuff at the operation space or at the task space, things will not be as easy as this. That's exactly what we're going to be doing next time. At the joint space, yes. Okay. So this is an error in the joint space, to be very precise, in the joint space. Okay. And this is something weird happened. I zoom out, right? Zoom. Canvas is locked. Okay.
No. Click on the zoom again, and then I think you can do it.
Okay. Okay. And let's bring it back here. Okay. Oops. Okay. Better. Let me clean this mess. So, to be again precise, we're going to be doing PD control here on Q, which is the joint space. The operation space will be next time, John. Yes.
Regarding the problem of the error to wrap around the angle, can we not just start considering that the angle is from 0 to 360?
Same problem. Same problem. 360 minus 360 minus 1.
Yeah, 359.
Okay, so do you want the controller to go 359 steps, or do you want to go with one step in the other side? That's the whole idea.
I understand.
Okay. So this is the error between the theta and theta desired. So what will be our potential function? Does anyone have a potential function in mind? The potential function psi, which is a function of theta. Any guess?
Equal to the gravity?
No. Gravity itself, let's leave it on the side. Let's think of something. How is we want a potential function that will be able to have theta desired as its minimum, something that will act as if, it will pull the system towards the theta desired. What did we do here when we had, what did we do and have here when we had SO3? We had the half trace, stuff like that, right? What did we do when we have the PD control on R3? It was a quadratic function of theta minus theta desired. We use exactly the same here, okay? So we have half theta minus theta desired transpose multiplied by some Kp. Kp here is some positive definite gain matrix that you can choose as you wish, multiplied by theta and theta desired. Make sense? What is now the proportional term? The proportional torque, tau p, we compute it simply as minus the gradient of theta of psi of theta with respect to theta. What is that equal to? Minus kp theta minus theta desired. Okay. Everything is back to Rn. Everything is easy. Okay. You all agree? Okay. Is this controller enough? Is this potential function enough? Okay. Now let's see. Let's plug in that and see what happens. Okay. So let's do a Lyapunov analysis. So part 2. Let's do a Lyapunov analysis. So the closed loop V, okay, we're going to be calling it V. And we're going to be choosing it as the V open loop, the one that we had earlier, which was also a function of x, plus this extra psi that we added, okay? Where the theta here, just to be consistent, is actually x1, okay? We just add a function here of x1. We did not do anything with x2, we just left it as is. And just to remind you what was the open loop part, it was the half x2 transpose m of x1, x2. We had also a part related to the potential energy, which was a function of x1, plus psi of x1. This is what we added here. Okay? Make sense? Now, in order to play around with this, we need to first make sure that, okay, if this is a valid Lyapunov function, that v of x desired is equal to what? We need to v of x desired to be what?
Should be x minus x desired.
No, it should be what? What is the value of this, of the function here? So v is always a function that is q and gives you r. Okay, in this sense, it's tq to r. So it's the state space. Okay. So after it eats x desired, what x desired, we said that our goal is to have theta desired and theta dot equal to 0. We want it to be equal 0, exactly. So if we plug in x desired here, what do we get? We get, first of all, what is our x2 desired? It's 0. Everyone agrees? And what is the E potential at x1 desired, which is the theta desired? What is that? Is it 0? Let's keep this to check it. What about psi of x1 desired? The psi of x1 desired, what is it? So if we go back, this function that we added, the psi, is equal to theta minus theta desired. If I plug in theta equal to theta desired, what do I get?
0.
I get 0. Okay? So this is equal to 0. So this part here, okay?
This provided that x desired equals 0. If it is not equal 0, it will not be like this, right?
Which one?
XD. This provided that x desired equals 0.
No, x desired is equal to theta desired and theta dot equal to 0. So theta desired can be any angle. I want the first joint to have angle 0 and the second joint to have angle 90. The first joint to have angle 20, the second joint to have angle 40, third joint to have angles 50, and so on. I think you can choose.
For the positive definite for the Lyapunov function, should be only at x equals 0 to be v equals 0, right?
It should be at the x star that you want, so whatever equilibrium point that you want the system to have. So we want to have the equilibrium point of the closed loop system to be x desired. This is our desired equilibrium point, the one on top.
But I know for the Lyapunov function, v of 0 should be only should be
V of the point you want.
to be assumed
V of x star, not V of 0. V of x star to be equal to 0, not V of 0 equal to 0. V of the x star, the one that you want, that it is an equilibrium point of the system.
So it is also could be something else. It could and also be asymptotic stable.
What do you mean?
Yeah, for example, here Vx desired or the equilibrium that I want, it could be also XD not equal 0, and also give me
What is the zero? What is the zero that you're talking about? Is it the value of v after it eats the x, or the x itself is zero?
So if XD, for example, any equilibrium point, if it is not equal to 0, it could be this V could be equal 0 and also asymptotic stable, right?
But that's exactly what we need.
Okay.
Exactly. We don't need that the equilibrium point is zero. We never said that. Otherwise, what's the point of control, right?
Because that one, it was a common one. V equals 0 should be equal.
It's for simplicity. Just, for simplicity. But in general, no. You can have any x desire.
Okay.
That's exactly what we want to do for control. Now, at that part, do we have that v of x desire equal to 0? Do we have a proof that the point that we choose will have gravity torque, have gravity potential energy equal to 0? Let's try to check that out. Okay, maybe it does, but let's try to do something. Okay, what is the gradient of E potential with respect to x1, with respect to the theta? What is it equal to? Come on, guys. It's the gravity torques. Okay. So for this to be equal to 0, then theta desired should be one of the equilibrium points of the system itself. Okay. So in general, if I want the robot arm to have a configuration that's not one of the equilibrium points, it's not possible to choose this Lyapunov function. It's not actually a valid Lyapunov function. Okay. I cannot, in other words, this potential function that I added is not enough. What do we need to do here?
The opposite of this.
Opposite of this, what do you mean by that?
For the E potential, we need sort of minus E potential function.
Exactly. That's exactly what we're going to be doing. So the solution to that problem is simply, for the Lyapunov analysis to work, it's not enough to choose this potential function. We need to add something to it, which is minus the E potential of theta. And thus, when I take the gradient of this psi function with respect to the theta, I get here also plus g of theta. Because the gradient of this, okay, is the g, and I have minus, so I have minus the minus, I get the positive
But
g.
we just added E potential of theta. Like, why did we add it?
E potential is the gravity. So in the end here, so if you look at this control law, it's simply I have a proportional term, but I also have, what is this term called? Does anyone know? Okay, can you think of something?
Gravity torques?
We don't call it gravity torque, because the gravity torque are the ones that are acting on the system. We call this usually we call this the gravity compensation torque. So if I don't apply any torques, there is some, if I don't apply any actuator torques, the gravity will take the robot arm, make it go down. But if I apply this term from the actuators, then the gravity will be cancelled. Gravity will be compensated. Okay? It's exactly the same idea of I have a drone and I put it in the air. Okay? Gravity will want to make it down. What are the propellers going to do? Counteract the gravity, cancel the gravity as if the thing is floating in the air, and then you call it a hovering drone, right? But hovering is simply what? Canceling gravity. That's exactly what we have here. From a Lyapunov analysis, we need to add that term such that when we have this expression here, so this will now be psi. Okay, so what is this term here? So let's expand this. We're going to have half x2 transpose m of x1, x2, plus I had here half x1 minus x1 desired transpose, which is theta minus theta desired, multiplied by some constant matrix x1 minus x1 desired. And then I had plus E potential, which is the gravity of the gravitational potential energy of the system. And I had here afterwards minus that. So I had E potential as a function of theta. And then I had minus E potential as a function of theta. So all of these two terms, everything that's in yellow here, is simply this psi of x1 that we added. that we chose. Remember, psi of x1 is a choice. You can design it as you wish depending on what you want to do. And that's exactly what we're going to be doing here. And what we get as a result is that these two terms, what will happen to them?
Cancel each other.
You cancel each other. And then we're left that when we substitute this expression here, what happens?
0.
This becomes cancelled out as well. So this goes to 0. And then we have that this is truly equal to 0. Make sense for everyone? Do you see the line of thought? Okay. So when you're designing a Lyapunov controller, it's always an iterative process. Okay. You either come up with the controller, you dream about it, or you plug it in, okay, and you just say, okay, it's stable. But if you remember what I told you earlier, that actually the stability analysis is part of the control design itself. Okay. Usually you try something, and you see what will happen, and then you modify the Lyapunov function and go on further. Yes, Fahd.
What if we have an external force that's constant in a certain direction, like a spring that's mounted at the end of the vector? Should we also put that in mind?
That's a completely different system.
Okay.
Whenever you start with the Lyapunov analysis, you make sure that you've already made all of your assumptions and you have something that you're talking about. Anything else you think about, what if, you're talking about another system. And you can extend stuff here. You can say, okay, this is the case when I have no external forces or no external torques or no external interaction at the end effector. What happens if I have that stuff? You can extend the analysis, but at least so far we assume nothing is there.
So it made a very different function here.
Whether we can actually have a function that will do that, that's another story. Okay, but that's why I'm thinking it's a different problem there. How do you treat it? Okay, we're going to look at it next time, inshallah. Any questions so far? Okay, so just to wrap up, so now the Lyapunov analysis. Now let's continue. So v dot, okay, of x will be simply equal to the gradient of v with respect to x1 transpose x1 dot plus gradient of v with respect to x2 dot. Everything is Rn now, okay? So I don't need to talk about you can, of course, talk about, okay, I have the differential of v with respect to x1, but in the end, it's just the transpose of this guy. And what was the v that we chose? We had a couple of terms here. We had, this is a function of x1, okay? So what we're going to be having here is simply, you're going to have m of, this is left for you to continue on the homework, okay? Because you're going to be doing the first part in the homework, okay? And then you're going to be saying, okay, you can extend it to the next part. I'll just tell you the final result, okay? Because I want to show you actually the implementation, okay? So the result is that after you do all of that, you're going to be left with something that looks like this. Plus x2 transpose tau d, okay? How do you choose now the tau d? First of all, do you need to have a derivative term? Think about it. If I put the derivative term equal to 0, what is the result?
We need a stiffness.
Sorry?
We need a stiffness. We need a part that mimics the stiffness.
The part that mimics the stiffness is given by this term. The part that cancels gravity is given by that term. And the part that we're designing now at this stage is what? The one that injects the damping. But the system itself has already inherent damping, right? And that's why we put the friction here from the beginning. So even if we don't put any friction, the system will always be stable. Will always be globally asymptotically stable to where you want, okay? So actually, assume that tau d is equal to 0. Then you can actually show that this is less than or equal to 0. It's negative semi-definite alone. How do I show it's negative definite? How do I show that actually it's asymptotically stable? LaSalle's invariance principle. Okay, and you can show actually that in the end, no matter what the b of x2 is very important. B of x2 is always assumed to be positive definite. Okay, there is no such thing as negative friction, right? Friction is always positive. Even if it's not linear, we always assume it's positive definite. Okay, so always we're going to have that friction is positive definite. This is usually the friction. Okay, it's because it's physical, and thus you see here I'm always guaranteed to have this term negative. Okay, semi-definite, and then okay with LaSalle you can actually show that x equal x desired is globally asymptotically stable. Okay, and the reason why it's globally asymptotically stable, okay, is that if you go back to the Lyapunov function, see what is the Lyapunov function that we have here? It's given by a quadratic function on x2 plus a quadratic function on x1, while the gravity term just disappears. So in the end, I'm left with something that goes, it's radially unbounded, okay, from x1 in the x1 direction and x2 direction, okay, and I have that the derivative of that Lyapunov function is negative semi-definite. With LaSalle invariance principle, you can show that in the end I have only one equilibrium point, the one that has x2 equal to 0 and x1 equal x1 desired. Okay, so that's the conclusion. Now the question is, why do we even need a derivative torque? Any ideas where you might want to have that?
Controlling the damping.
Control the damping. What do we mean by control the damping?
For example, damping it will have some settle time.
Exactly.
Control it.
So here we said that we have a mathematical proof that the equilibrium point is globally asymptotically stable. We have no idea about how fast is this, right? It can take forever. Okay, it's asymptotic. What does asymptotically mean? It means as time goes to infinity. But sometimes you might have some particular requirements on the, on the settling time or on the performance of the system, and then you might actually need to have, I need to have fast damping or slow damping, okay, depending on the behavior. Okay, so in real life, actually, what we're going to be doing, we're not going to assume that tau d is equal to 0. You're going to actually choose that tau d is equal to minus kd multiplied by x2. Okay, if you plug in that here, what this term becomes is x minus x2 transpose b of x2 plus kd multiplied by x2. And you see here, okay, because of this kd variable, I can control how big or small this function is negative definite, okay? Negative semi-definite at least. Okay, so I can control how fast does v dot go to 0, okay, just because of this kd term. Initially, I was only relying on the b, okay, so it depends on this b if it's big or small. Now I can control the damping. I can change the damping of the system, okay? So that's it. So actually, any questions?
What is the KP again here?
KP, where is the KP? The KP was, so what is the control law? So this is the damping term. And this is the proportional torque. Okay? So I have minus Kp multiplied by theta minus theta desired, and I have the gravity torques. I compensate them. I cancel them. I cancel the gravity. Okay? This controller we just derived has a very simple name. It's called PD plus gravity compensation. Full stop. Called PD control plus gravity compensation. So let's save this. No, let me share again. So let's go back to the slides. Okay, so this is the controller we have. Okay, so summary, we have that the proportional term is given by this expression, and this is the derivative term. So you see here, this is P control, D control, plus gravity compensation. You plug in that stuff into the closed loop system, it becomes like that. Okay, and it is you can easily show that it's a globally asymptotic equilibrium point. Okay. And by the way, you don't even need to do Lyapunov analysis for that. Okay, to show that it's actually positive. That is. Actually, no, yeah, you do need Lyapunov analysis because it's still nonlinear. Okay. So you see here, I have the C of x, the B. I did not change them. I did not remove them. They are still there. So I have a nonlinear equation. I have a nonlinear state space model, and still the global asymptotic stability is valid from the choice of the Lyapunov function we chose.
The nonlinear here, it is in the C, right?
C and the B. The B itself can be in general a nonlinear function of the friction, of the velocity. Sorry. So now let's go to MATLAB. Let me show you around how this will work. Okay, you'll have this to play around with at home. Okay. So our favorite tooling robot arm. Okay. Slider for desired theta 1, desired for desired theta 2. The proportional gain and the derivative term gain, you can play around with it. You can start and stop the simulation as you wish. Okay. So the controller will always be running. Okay. So let's press start. Okay. So you see here, the controller is just, the angles are zeros and the desired values that you want to go are zeros. So let's choose, for example, theta 1, have some angle. Okay. And theta 2, to have another angle. Okay. You see here, okay, the simulation itself is the one that's slow. Okay. But eventually, theta goes to theta desired, and theta dot goes to 0. Theta 1 dot goes to 0, and theta 2 dot go to 0. Okay. We said asymptotically, so you see it's just very, very slow. Okay. And the gains, you can play around with this performance, depending on how fast the system you want to go. Okay. Let's choose, let's boost a little bit the gains of Kp. Let's make the Kd a little bit higher. Okay. And now let's change, for example, that we want the theta 1 desired to be this value. Okay. You see here in the beginning, for example, we took, I don't know, like almost 2.5 seconds to stabilize. Okay. And here, something happened here. What is it? There was a very big overshoot. How do you play around with this overshoot? You can play around with the damping. And that's exactly the whole idea of you control the damping. Okay. So you see here, this was the overshoot that we got from this gain. So let's maybe pump it a little bit. Okay. And now let's try to give it a big jump again. So let's increase this one. And you see here, we played around with, okay, there was almost no overshoot here. It was actually pretty good. Okay, so you can play around with the gains. Okay, if I choose the KD to be 0, do I still have stability or not?
Yes.
That's exactly the result that we said, right? Even if I have KD equal to 0, with very high, proportional term. Let me see. Did I put? I think I did not put the friction here in this simulation, so you can actually play around with that at home. But I don't think I have friction here, and this will not actually be stable. It will not be globally asymptotically stable. However, it will be stable. What does stable mean in that sense? It's not going to be pretty, but we'll see. Okay. So this is what stability means. Okay. Okay. Theta minus theta desired. Okay. Okay. You start from a trajectory near the theta near the x equal x desired, but it keeps on roaming around it. Okay. So it never goes to it. Okay. Because again, just to remind you, there is no friction here. So B of x2 in this simulation is equal to 0. Okay. If I added the friction, you would have seen, this, okay, all of this oscillation to damp out. Even if it's very slow, okay, it's still called global asymptotically stable. However, this is not global asymptotic stability. This is just stability. Okay. Okay. Now we choose the gains. So let's pump it up immediately. You'll find that it should stabilize at the value, okay, that we chose. okay? That will just stabilize here. Okay? You see the whole idea of actually deriving, this is one of the very, I hope you got out of the course is that one of the key things about thinking of the PD controller is that it's something related to stiffness and damping, is that it makes your life tuning this stuff very easy. Okay? It becomes very intuitive to actually go to the experiment and look at the thing, and imagine that there is a spring there. Imagine that there is a damper and you're tuning the spring and the damper. Okay? Even if you have something very complicated like SE3, okay, you can still imagine there's a spring and there's a damper and you're playing around with them. Okay? And this idea of looking at the PD controller as a spring and a damper goes way beyond just doing control. Okay, you can even extend it to a lot of scenarios. Okay, you can start to do interaction with it. Next lecture, inshallah. You can even do teleoperation with it. With haptics and stuff like this. If you just start imagine that you have springs and dampers. You can even combine springs and dampers. You can do collaborative manipulation in this way and so on. So you can really go crazy, and it's all very very simple. Just PD control. And you see here we increase the damping and things became stable. Okay. Any questions? Anything you want to see here? You're curious before going home? You're gonna have this at home, so you can change it as you wish. Yes.
In terms of tooling manipulators, it starts making sense. Let's say we have a mobile robot. We can still assume, let's say the wheels or whether it's mechanical wheels or other wheels, we can still assume it as being the springs and play around with the damping and the proportional gains as spring constants?
Forget about the wheels. If you have a mobile base, think of the whole base on the ground as just one rigid body attached to the ground with a planar joint. So it's allowed to move everywhere, okay? And you just have, it's and in the end, the forces that you wanted to move with, you can do a control allocation to say, okay, I want this wheel to move with this speed and this wheel to move with that speed, or this torque and so on. You can usually do it the other way around. Exactly what we did with the drone application last time. We designed a controller for a wrench on the whole rigid body, and then we transform the wrench. We say, okay, this is the desired wrench I want. What are the actuator inputs that will give me that wrench? Okay, we separate the problem. Okay, so if you're satisfied, so let's wrap up with one last part on feedback linearization. So, who's familiar with feedback linearization? Okay. Who's not? Okay, 0, 1, 2. Okay. So feedback linearization is something that, very easy to think about. Okay, it's like the bread and butter of many people that don't know how to do control. Okay, so it's very easy. The whole idea is that I have a nonlinear system with nonlinearities. What do I do with it with the controller? Kill the nonlinear terms. Full stop. You have control. I did modeling. I know what the nonlinear terms are. Why don't I cancel them? Did we do something like this now?
We did the gravity compensation.
That's exactly what we did in the gravity compensation, right? You see here in this controller, you see what we have here is that x minus x desired, right? So x1 minus x1 desired. So theta minus theta desired. In order to implement this controller, I need to tell the controller what is the theta desired. We give it here with this UI now. The theta 1 and the theta 2, they are feedback, right? I just measure from the system. I measure the angular velocity and the angular displacement of the joints of the robot, and I just feed them back to this controller. And I multiply them by some gains. So everything is so far so good. But I also have the G term. What is the G term here? The gravity term, the gravity torque. What are the gravity torques? How do I get them? How do you get the gravity torques? If you go back, but you need to go really back, you remember that we had an equation for the gravity torques, right? I had the G of x was equal to, there was something that was taking the gravity in the spatial frame, and I multiplied it by some adjoints, and I multiplied the inertia. There was an expression there when we assumed that the gravity was, that the whole inertial frame was translating up, it was moving up. We had an expression for the gravity. So if I know what the robot looks like, I can always find what the gravity terms look like. They're not usually going to be pretty. Okay? There are efficient ways to actually do it. MATLAB does it in an efficient way. There are packages online, in robotics people are using that can actually give you the G of x. But you need to give it the theta, okay, which is I measured it already, but in the end it will give you the torques. And for example, just to remind you, we already had an example. So this was, for example, the gravity torques in the case of a two-link manipulators. In order to have it, I need to know that there's, for example, sine of theta 1, sine of theta 2. There's no big deal about the signs. What is the real problem here? The gammas. Where do the gammas come from? What do you think the information inside of the gammas will be? The mass of the links. What else? The lengths.
The matter itself.
Matter. The center of mass location, where is it? In the joint frame and so on and so forth. So inside of the gamma 1 and gamma 2 here, I have physical parameters of the system. Do I know these physical parameters or not? If I give you the robot, do you know them?
To an extent, you don't.
How?
We can measure the length of the system, of the links.
You can measure stuff. What about the center of mass?
Yeah, that's why I said to an extent we know these.
So to some.
Model it.
Sorry?
Physical modeling, yeah, basically. Like,
If you have CAD modeling, exactly. If you already designed the CAD model, but if you have a robot, who does the CAD model? You as an end user or the manufacturer? The manufacturer should do the CAD modeling and give it to you. If the manufacturer is nice, he'll give it to you. If not, you're on your own.
We need 3D scanners then.
You need to do something. And that's why there's a whole field on its own. A lot of people have worked on this. You can take the robot arm, itself, and try to identify the inertial parameters from the experiments, from the torque and joint measurements. You can do that. And a lot of people are working on that. And in the end, you just have a identification problem, system identification problem. You need to solve the least squares. But even that, there's a lot of stuff on geometry there. So if you're interested, I can tell you more. So the bottom line is that just knowing the G, putting it in the controller, from a stability, from an analysis, from an implementation point of view is no big deal. From an analysis point of view is no big deal. When I go to the implementation, I need to know exactly what the gravity looks like. So the bottom line is that we already used some compensation of the system dynamics here. What feedback linearization does is that it even goes way beyond this, what we did. It simply tells you that I'm going to kill the whole dynamics. I'm going to invert the whole system dynamics, assuming that, and I'm going to make it in the end something that's linear. And if I have a linear system in the end, linear controllers, basic stuff, everyone should know. Every control engineer should know. So if you have a state space model given by that equation, I have x1 dot is equal to x2. The first equation is already linear. I don't need to do anything for it. x1 dot is equal to x2. x2 multiplied by 1. And x2 dot is equal to m inverse, nonlinear, multiplied by c, nonlinear, b, nonlinear, g, nonlinear, and have the torques. What is feedback linearization? What it will do? Shows that the torque is equal to g plus b plus c. So g plus b plus c. And then afterwards, I multiply here by an m, so the m will cancel the m inverse. And I'm going to be left with, in the end, something that looks like minus kp multiplied by this term plus kd, minus kd multiplied by that term. So I'm going to transform this highly nonlinear system to something that looks like this. x1 dot is equal to x2, x2 dot is equal to minus kp x1 minus kd x2, plus some extra term for the theta desired. Became very linear system. I can easily do, linear analysis for that. I can design the kp and the kd, assuming everything is linear and so on and so forth. However, I need to know here, in this controller, what do I need to know? G, B, C, and the M matrix. I need to know everything. This is usually known in the literature as the computed torque control method. CTM, computed torque method, or in general, this is just one way of. This is only in the robotic literature. They know it as the computed torque method. However, if you in nonlinear control, this is just simply known as feedback linearization.
We don't need to know the G, B, and C because they will cancel each other when we do the feedback linearization.
Take a look at the controller here. This is what you implement. So in order to implement this on the computer, I need to have all of these terms. So I need to know them. They cancel because I plug them in. It's because I know them, I put them in the control law, then I already canceled them in the closed loop system.
I thought that I meant that we don't need to know
design is in our hands. Anything that is in the control design, we need to know related to that. So if you don't know the value, like for example, it's a game. I don't know it's supposed to be 5 or it's supposed to be 10. I cannot insert the value of this in the controller.
Clear? So I need to know these terms. I need to plug them in. They are torques in the end. They are a variable of x1 and x2. So at every value of x1 and x2, I need to give, what these expressions are. Okay?
But how can we solve the problem of the uncertainty or tolerance, the system identification?
Exactly. System identification is another thing. Okay? But here, if you just compare this computed torque and the PD with the graphic composition that we did, you'll find that there is a huge difference. First of all, in the computed torque method, we have full dynamic compensation. I'm compensating everything. Okay? Here, I'm only dynamically compensating, the gravity torque. That's one thing. Here, I need to know exactly my model, which is equivalent to knowing exactly how the robot looks like, which goes to the parameters problem.
And this has some solution practically?
Yeah, system identification.
Can work, but any system identification cannot give me, there will be some residuals.
Exactly. So even with the system identification, so whether I do system identification or I do CAD modeling, or I think of something, I will always have something in general called parametric uncertainties. There's always something called parametric uncertainties. That's one. There's even something worse than that people usually rarely look at, something called modeling uncertainties. For example, I design a robot assuming, for example, I have no friction. And if I know what the friction is, I'm going to assume, for example, viscous friction. Is this the real friction model? No, it's actually called the model. It's an assumption. What about gears? What about the power electronics that's going on? What about the temperature? You say negligible. Is it? That's the thing.
So is there practically, not a simulation, practically a solution?
Yeah, so practically, the controller, two things. First of all, this controller requires all of this knowledge, which means that it's highly sensitive to any errors that you do. The controller that we have here in the gravity compensation is less sensitive to that. I don't need to know all of this information. That's another advantage. Now, in terms of performance, which one do you think will have a better performance?
The first one.
Provided I know exactly what the parameters look like, this one will actually be able to achieve fast and high dynamic performance. While the lower one, I cannot really get that much performance because I still have all of these nonlinearities that will slow me down. They are usually, sometimes they might counteract the motion I want to do. So in real life, actually this is better because when I'm using the controller, I am introducing less errors into the controller problem. Okay, that's one thing. Now, in order to augment the performance of the system, you can have another field of research, which is how do I reject the disturbances that come from the modeling uncertainties and the parametric uncertainties. So you need to design either this is only PD term, this is only PD controls, which means I don't have anything with integration, and this is where I can have the integral term. There are even fancier ways than just doing integration. Okay? You can do something called disturbance rejection, okay? And I can have a disturbance observer. I can use force and torque sensors to improve that stuff, and so on. Okay, so there are more ways to actually improve this. Yes, right.
The computer torque method, does that mean that people have to remodel the system after a while? For example, if the system got worn down or there's a problem with the power electronics, does that mean that every time they run the system they have to remodel?
Wearing is usually at a very low scale compared to actually knowing the dynamics right now. Okay, so if it's every month and every year, this is not the problem we're talking about. The problem is that I don't even know them. We bought the robots, we have them in the lab. I don't know what the parameters are. How can I control it? That's the problem. Okay, I give you the bunker, for example, for you have the bunker or you have the robot. I give you the robot. And I tell you, design the control. You tell me, I don't know. If everything in simulation is nice because you have the RDFs that you have, they are filled with numbers, right? The lengths, the center of mass, okay, the mass of every link, and so on and so forth. The coefficients of the friction, coefficients of the stiffness, and so on. So all of the simulation is completely away from the real life. Filling in the gap is another problem. Okay, so it's part of the research. Okay, yes, Asha.
When we are doing mechanical design, we introduce something called factor of safety. Is it possible to do similar thing in the control design?
No, it's not, because factor of safety is usually that the thing will not, break and kill someone. Here, this is performance. For example, if you're not satisfied with this performance, what do? You just pump the gains. And there's something I haven't discussed here, which is, why not choose the gains to be the highest possible?
The control effort.
Control effort will be problematic, right? I'm going to get high control effort, right? What about what's the problem of high control effort? Saturation. There's even a worse problem that you usually, rarely again, people look at.
Power consumption.
No.
Not safe.
Sorry? What is not real?
We cannot apply it.
Let's say that you can even apply it. So again, this is the saturation problem. Let's say that it's within the saturation.
Damage the
Safety issue?
No.
damage the equipment itself.
Sorry?
Damage the equipment itself.
You're almost there. Why?
It will introduce vibration in the system.
Exactly. It will introduce vibration into the system. For these robots, usually, this idea of modeling, stuff that you did not model. None of these robot arms, they are fully rigid. Okay? And it becomes even worse as you go into applications, for example, if you have a drone. If you want to have a robot arm on a drone, it's impossible that I can design the robot arm to be very rigid. I need to make it flexible. And flexibility means actually that already the system itself has stiffness on its own. And the equations of motion we derived don't take that flexibility into account. The joints themselves, they can be flexible. And this will introduce all of these high dynamics. You're going to be going into the region of actually the resonance modes of the structure itself, which means that you can actually, in the end, I can have a high control effort will correspond to high frequencies in the controller. High frequencies will resonate with the high structures, and you can damage the controller. You see that clearly when you go to applications when you start to have interaction, and that's exactly what we're going to be doing next time. Or you start to have delays in the controller if you want to implement this controller over the internet. Or if you want to have haptics, for example. All of this stuff, they start to play a role. In the simulation, you never see that. Okay. I hope I convince you now to stop doing stuff with the simulation, okay? So let's stop here. Jazakumullah khair.